Welcome back again. I hope you're refreshed and rested. And I'm pleased to introduce our next speaker, Professor Andrea Bosato, who is professor at the University of Newcastle in Australia. Andrea is an expert in karst and cave studies, Speleothem petrography, karst hydrology, geochemistry, quaternary geology, paleoclimate reconstruction from continental carbonates, and trace element analysis. Since 2002, he has pioneered synchrotron XRF and XNAS analysis of continental carbonates, becoming the world-leading expert in the field. He has participated in the past S4 summer schools, and we are very happy to welcome him again. Please, the floor is yours.
Thank you. So, we designed this lesson and workshop in two parts. So, in this lesson, I will give you the basic concept of Speleothem petrography, whereas in the workshop, we will see how to construct a petrographic log with our samples. So the presentation outline starts with the nucleation and growth of calcium carbonate minerals, and then we will see quite quickly the different types of carbonates, speleothems, mummy, calcareous tufa, and spalitic crystals, and the environment of formation. Then we will focus on calcite speleothem fabric, which is the main topic of the workshop, and we will discuss about the diagenetic modification, including aragonite to calcite transformation. During the workshop, we will tackle the petrographic log and the optical properties of calcite fabric. So, as you already know, the mineralogy of speleothems is mainly made by carbonate minerals, aragonite, calcite, although there are rare speleothems that are made of hantite, a magnesium carbonate, or halite, gypsum, opal, but are very rare and are not very much utilized in paleoclimate reconstruction. So basically we are dealing with aragonite and calcite, which are the polymorph of calcium carbonate, respectively the rhombohedral and orthorhombic phase of calcium carbonate. So there are lots of investigation methods. We can start in the cave with calcite farming experiment or aragonite as you like. Of course, we will use optical petrography, but also we can use high resolution scanning. We can use confocal and fluorescent microscopy, synchrotron XRF, and electron microscopy, scanning, transmission, and atomic force microscopy. But in this presentation, I will just focus on optical microscopy with a short overview of the other methods. So calcium carbonate polymorphs are, they have different stability and different gravity. The only stable phase is calcite. All the other phases are unstable. And amorphous calcium carbonate and vaterite are highly unstable. In a matter of minutes or hours, they tend to transform into calcite. Also, aragonite, in theory, is unstable, and on a million scale here, tends to transform into calcite if the condition change in our speleothem. Of course, if the speleothem is sealed, it can stay intact as aragonite for a very long time. So as we can see here from nucleation and growth experiment, the first phase we can nucleate amorphous calcium carbonate that will aggregate into clusters of vaterite, and eventually in a matter of few minutes they will transform into calcite. And talking about the nucleation theory, there are two broad different types of theory. The classic nucleation theory, which is addition, monomer by monomer, ion by ion of species, so a calcium ion and a carbon ion attached at the growing solution. And this is typical of columnar crystal. And this can have the problem of differential incorporation, as we have seen in the sector zoning for strontium, because strontium being an acute, a large ion, tend to prefer obtuse angle and obtuse sides, so it's preferentially incorporated on the obtuse sides of the growing calcite. On the other end, we have this novel non-classical nucleation theory, which during the pre-nucleation and nucleation, we do not have ions, but we have particles and clusters. So you already have nuclei of molecules that can aggregate in cluster and eventually transform into two different amorphous calcium carbonate, and then finally into these stable phases. These precursor phases, in some exceptional circumstances, can be preserved in our Speleothem samples, but we have to look for them very carefully in order to detect them. So these are lots of different crystallization pathways, and we will discuss this monomer by monomer, the classical nucleation theory, and the non-classical nucleation theory that group all these other different pathways, passing through the unstable phases down to the final calcite crystal. So a very simple way to approach crystallization and growth in our case is performing calcite farming experiment, not just for the stabilized laboratory element composition, but for the shape of the crystal. And so this is the first experiment we published back in 2000 at Gorta del Nesto in Italy, where we farmed during 2 different seasons the calcite crystal. So during late summer and spring, the water is at low supersaturation, around 0.2, and the product of farming are these very nice rhombohedra with stepped faces and very few defects. On the other end, during winter, we have more ventilation and more supersaturation, and so we have a combination of rhombohedra and scalenohedra with a stepped faces and elongated along the flow direction. So it's a much more dynamic and complex crystal with respect to the rhombohedra. And we can perform in cave, in situ precipitation, instant precipitation experiment. We use TEM grid, we use the very water forming our Speleothems, and we can precipitate in half an hour the very precursor phases of our calcium carbonate. And we were able, in this cave, in Italy as well, to have vaterite forming on our TEM grid. Of course, yet it has to be analyzed quite quickly because it will transform into calcite, but still you can freeze the growth with and observe under the transmission electron microscope. So these experiments are very useful to test the precipitation environment, and some are very simple. So just analyze under SEM your calcite crystals, and you can have a good hint about what happened at the Speleothem surface. So the implication of these different 2 pathways is that there are multiple mechanisms of crystallization, and if we are dealing with non-classical nucleation, we are dealing with a differential incorporation of the trace element that can adjust in extra-lattice site. So we can have, like in this synchrotron XRF map, we have strontium in red, which is preferentially incorporated at the crystal boundaries. So it's a differential incorporation because we are dealing with these blocks that can be arranged quite nicely and differently with respect to the columnar crystals. So, as a first summary, we can say that both classic and non-classical nucleation pathway may contribute to the final columnar calcite formation. And columnar calcite nucleate via classic nucleation at low magnesium ratio, low supersaturation, and low organic content. These are the basic standard in order to have columnar crystals. When you change the condition, so we rise the magnesium ratio, we shift towards the aragonite field. We rise the supersaturation, and we can have the metastable phases, and we can have also this shift towards final disequilibrium phase. So these are the ideal equilibrium condition, not from an isotopic point of view, but from a crystallographic point of view. So what happened in the cave, you should know already, but I'm talking about the different Speleothem types. So not just the fabric, but the morphology of the Speleothem. And we divided in 3 broad categories, depending by their density and their water content and porosity. At the lower end of the scale, we have mummy, which is very plastic and full of water. The intermediate is tufa, which is still soft and very porous. And finally, we have spalitic Speleothem, which are dense and compact, and with a very low porosity. So, in the study of the alpine setting in Italy, we studied different caves at different elevation that have a different mean annual temperature, and because of this, we have a different soil CO2 and a different calcite supersaturation in the drip water. At high elevation, the water is undersaturated, we just have dissolution, but when we reach the alpine Mayo plain, we start reaching the saturation for the drip water. And there, at 0 supersaturation, we need something more in order to promote the calcite precipitation. And this something more is the biomediation. So mummy is a product of biomediation of very low supersaturated drip water. Then, if we move down and we increase the mean annual temperature, in the inner part of the cave, with less ventilation and stable temperature and relative humidity, we have our Speleothem. When we have a higher ventilation and a higher energy, we can have calcareous tufa, especially near the cave entrances or when we have a high flow of water. And these are how they look like. So this is calcite mummy under SEM and a transmission electron microscope. You can core just hammering a tube in the deposit, and is made by this filament nanofibrous crystal that can eventually transform into rods, serrated rods, and polycrystal. Then we have the calcareous tufa, which is typically made by this very fine and irregular laminae that are made of clear or clearer calcite and high organic rich calcite. This darker layer are high in organic and high in trace element and metal. And these are the thin section, and these are the SEM picture. So it's really a mess of different little crystals combined together. It's not a single order crystal. And you can see how fuzzy the crystals are with respect to the columnar crystal that we will see in the other pictures. So spalitic Speleothems are the denser and low porosity Speleothems. So they tend to grow from moderate supersaturated water above 0.2. 0.2 is the minimum, up to 1, and are largely controlled by inorganic process. This doesn't mean that we do not have organic in the Speleothem. It does mean that the organic do not interact in the calcite formation or not match. So it's mostly an inorganic process. And we ordered the different fabrics. So in order to analyze the Speleothem fabric, Silvia Fritzer developed in 2015 this table ordered as an increasing degree of equilibrium in terms of crystallization. So the more equilibrium fabric is columnar fabric, and we will see. And then, as I said, as we change the condition, we rise the magnesium ratio, we can have the fascicular optic or the radiaxial calcite, and then we increase the supersaturation and we increase the ventilation, we have the dendritic calcite, and then with a high organic content we have the micrate bands. And finally, at the lower end of the scale, we have the diagenetic feature, which are microspar and mosaic calcite. These are diagenetic features that are diagnostic of a recrystallization in our Speleothems. So, what are the factors controlling fabrics in Speleothems? Well, as usual, there are many of them, and the combination can be really confusing. So there are no single factor controlling the fabric. The more important one, as Max showed, are alkalinity, supersaturation, and drip rate. So these are the most important factor. But then we can have the trace element, as we have seen, the organic matter content, the temperature, and the presence of detractor particle or precursor. And finally, of course, the diagenetic history of our Speleothem. So, in terms of mineralogy, the first and the broadest distinction is between aragonite and calcite. So typically, drip water composition is as a magnesium calcium molar ratio lower than 1 and a low to moderate supersaturation. So these are typical drip water analysis, and in this field we just have calcite. In order to have aragonite, we have to increase the magnesium calcium ratio above a threshold that depends by different factor, can be 1.5, 2, or like in this laboratory experiment, 2.5. So above this composition, we have just aragonite. But in a rare case in which we switch between the threshold, we can switch between calcite and aragonite in a matter of layers. And of course, we can also have recrystallization when from the aragonite layer we switch to the calcite forming water. So, columnar fabric. This is the most typical and common fabric in Speleothems. And we describe a different type of columnar fabric. You can find this table in our paper 2010, and they are divided depending by the optical properties and by the porosity. So the most typical, the end member equilibrium fabric is compact columnar. This is the typical and most common fabric in Speleothem in deeper part of the cave with very low ventilation and higher CO2. So when we have a low supersaturation, this is a typical product without any impurities or few organic content. So columnar is made of this elongated crystal with straight boundary between one crystal and the other, elongated perpendicular along the growth layer. Of course, when we have a nucleation horizon, like here, this is a growth interruption, a hiatus of a few thousand years. And of course, along the hiatus, we have tiny particles that act as nuclei. So the Speleothem has to renucleate and start again from that surface. So some of the crystals go through the discontinuity, but some mother just renucleate. So these tiny crystals are not a different fabric, are just the initial phases of the columnar fabric. And then, because of the geometric selection, only the one oriented perpendicular to the growth surface will survive. On the other end, columnar can has this broad differentiation. So we have these are the end member fabric. We have the compact without porosity, and the open, which is the best for fluid inclusion, which has a partial coalescence of the crystal, and in between the crystal we have porosity that can be filled by inclusion, but also by void as well, or it can just incorporate detrital particle as well. So this is a typical thin section of Speleothem with an alternation of compact columnar and open columnar, and we can see in the if we made a zoom into the columnar fabric. So this is the polished section. The whitish band are the open fabric. The translucent one are the compact layers. And these are on parallel line, and this is under crossed color. We can distinguish between open and porous fabric. Open fabric is the most typical, in which the porosity is made by vertical alignment of intercrystalline boundaries, is where the fluid inclusion are located. But also, so is in between the crystal boundary. But also we can have porous layers that are continuous along the growth laminae, like this darker band here, and are made by a higher density of nuclei, so are slightly a micro-renucleation horizon. And of course the environmental significance is different with respect to the open fabric. Then we can add ingredient to our recipe and see what happens. So one of the ingredients is organic matter, and when we have a lot of organic matter, especially during pulses of flashes of organic from the soil, or during changes, seasonal changes in the redox condition in the aquifer, we can have the formation of organic lamina. These are visible laminae under the thin section, and of course they are also fluorescent, but not all the fluorescent laminae are visible. So the visible laminae are, I would say, a quite rare case, maybe 10% of the Speleothem we analyzed. But most of the Speleothem are chemically laminated. So if the resolution of our analysis is enough, in many cases we documented in all the climate setting from the tropic to the cold area a chemical annual bending. And if we have the organic laminae, we have all the metal elements like zinc, copper, yttrium concentrated along the organic layer. And along this organic layer we have a depletion of strontium. So strontium and organic are fighting against. They are enemies. And for this reason, we can just use strontium for the lamina counting. But we can combine the lamina counting with many other elements, and this will give a much more robust data. We can see how the columnar laminated fabric looks like. We start adding this more rugged extinction domain, and this is the shift towards the microcrystalline fabric that we will see later on. But also we can have an intermediate fabric between open and compact, and are the typical lamina couplets, first described by Gentil and Kniff in 1996, in which we have one layer, one seasonal layer in this case, made of compact columnar, which is typically translucent here, with low porosity, and it does correspond to a dry drip rate and the dry season. And then we have the open columnar that corresponds to the higher drip rate, and of course we have all the intercrystalline porosity within the crystal or the subcrystal. So these are the mesocrystal, this extinction domain, but within the mesocrystal we have all the subcrystal with the open fabric. And this has been documented in many other cases throughout the world, but also we can have not just annual couplets, but we can have, in most of the cases, are not annual couplets, but are couplets of band. So we can add lenses, multi-decadal lenses of more porous and multi-decadal lenses or more open compact fabric. But the hydrological significance of this fabric is still the same. So compact is dry and open is wet. This is a broad classification that we tested in many settings, from the tropic to the cold area, and in most of the cases is working. So when we have a Speleothem made of an alternation of open and compact, this is a very good paleohydrological record that we can use. And this is one of the examples. This is from Farage et al. 2022. It's a modern Speleothem covering the last 400 years, and you can see these bands of compact and more porous open fabric. And these are the stable isotope. In red we have carbon and oxygen, and we just use the end member because in some cases we have the stable isotope sampling just is in between two different layers. So we distinguish the end member porous and end member compact, and this is the cross plot of oxygen versus carbon here. So at fast and we compare this stalagmite composition with our farmed calcite experiment. We use also in this case end member terms. We have a fast dripping farmed calcite and a slow dripping calcite farmed. And of course they have a very different isotopic composition, with the fast dripping that still reflect and are in quasi-equilibrium with the drip water, whereas the slow drip morphology, they have a much higher oxygen and carbon isotope composition. And the corresponding fabric within the stalagmite just reflect this situation. So these blue and red ovals are the average area of the two end member fabric. So the compact fabric here in blue and the open fabric in red. So this distinction is the bread and butter of Speleothem fabric. You can use, of course you have to test it, but it's really the very basic as a start. And as we will see in the workshop, we can do on the polished slab. We do not need thin section in some cases. So this is the good news. We can do petrography just using the slab, the high resolution images. So moving ahead, we have the more disequilibrium fabric, dendritic, micrite, and finally the mosaic. And these are all the environmental parameters that are controlling the information, but we will just go quickly through them because you can have all the information in the literature. We will see the columnar microcrystalline, and as we have seen with the calcareous tufa are very similar. So this is a stalagmite from Grotta del Nestro, and this is a calcareous tufa Speleothem. So the fabric are similar. We have laminae, very rich in organics, and very tiny crystal combined in different aggregates. And we have this patchy extinction, so the crystals are more irregular, and the extinction is not uniform, is patchy and fuzzy. And if we look at the transmission electron microscope, we can see that are full of defects. And these defects in the calcite can accommodate all the junk that can be trace element, can be organic, can be everything. So the less defect, the less of this junk is eventually incorporated in the stalagmite. If we rise all these organic, detrital, and colloidal particles, we will move towards this more fuzzy fabric. And then we have the dendritic fabric, which is a high disequilibrium in terms of crystallography because it requires a high ventilation and in some cases also evaporation. And you can see that the fabric is a kind of boxwork of branched crystal, and we can have a fully open dendritic. In this case, we have no fluid inclusion, it are just voids, or a compact dendritic in which the porosity is partially filled by calcite. This is one of the worst fabric to work with because it's very prone to recrystallization, it's very prone to uranium leaching, so it's better to avoid if you have in your record, especially for uranium thorium dating. And then, when we have lots of organic, we have the micrite. And micrite are this very dark brown band that we have in the Speleothem, high fluorescence and epifluorescence. And here we have nested all the trace metal, and the crystals are very, very tiny. And micrite are usually concentrated along condensed hiatuses, condensed intervals, and hiatuses. You can see on the polished slab here, and we will see in the thin section here this micritic band, and the interval between here and there is more than 2,000 years. So it's a very condensed growth in which we have all this accumulation of organic laminae. Okay, finally the diagenesis. I will just go very quickly through it, and I will talk just about the destructive diagenesis, which is aragonite calcite recrystallization, but also dissolution and precipitation from calcite to calcite. But we can have also mimetic and cryptic diagenesis, which is very much more difficult to detect, that can remobilize trace element, especially uranium, but also can protect our Speleothem and seal it completely before the time being. So this is the typical aragonite to calcite recrystallization, and usually it proceeds in steps when we change the drip water composition, and we can have this relic of aragonite within the equant calcite mosaic. And so the equant calcite is the final product of the complete diagenesis and recrystallization. So it's really a diagenetic fabric. But as I said, in most of the cases, we can still see a remnant of aragonite needle or calcitized aragonite needle within the equant mosaic. And this is how it looks like. So these are the relics, and these are the euhedral, rhombohedra, which is the final product of the diagenesis. Okay, so these are few take-home messages. We have seen that we can use very simple calcite farming experiment to test the nucleation processes that are active in our cave. And this will tell us about the crystallization pathway in this particular cave or speleothems. And this different pathway can have a different incorporation for especially carbon isotope and trace element as well. So we have seen and we will see that each speleothem fabric has a distinctive environmental climate significance. However, as for trace element, this has to be tested cave by cave and stalagmite by stalagmite. So there's no simple rule that you can use to extract the environmental information from the stalagmite fabric. And for this reason, I want to stress, as usual, at the end of my presentation, that any robust paleoclimate interpretation should include petrographic observation as a start to check for the presence of diagenetic modification, but also for non-equilibrium fabric. So this should be really the starting test of our speleothem analysis. Thank you.
Thank you very much, Andrea. Now we have time for questions. Yes, please.
Micrite.
Yeah.
That's interesting. I have a marine background, right? Micrite for us would have been bacterial.
Yes. Yeah.
And is this how you look at it as well in this case, that you may have bacterial degradation of originally columnar fabric?
Yeah, usually what happens is you have during a hiatus, a stop of the growth, or a condensed interval, you have a colonization of the surface by bacteria and junk. So it can be anything from dust to black guano or growing bacteria.
Yeah.
And this, if you do not have calcite accumulating, they will just pile up.
Yeah.
So the micrite are a condensation of all the organic dissolved in the water in a single layer.
Other questions?
For nucleation phase, we study on the calcite, columnar calcite. So what about aragonite, nidronite, aragonite, calcite? Is it the same nucleation phase that aragonite goes?
Aragonite,
Can you repeat the question?
yeah, asked about the aragonite nucleation processes. So aragonite, because it requires a high magnesium to calcium ratio, this is the prerequisite for having aragonite. And with respect to calcite, aragonite has just this acicular fabric, usually. So it doesn't have the variety of fabric of calcite. So you start with this acicular fan-like distribution, and that's it. So if you nucleate aragonite, will stick to aragonite until the water equilibrium switch to a calcite, and at that point you can either start having calcite precipitation or aragonite dissolution and reprecipitation into calcite. So in order to seal the aragonite or to preserve the aragonite in a stalagmite, the chemistry of the drip water has to stay above the magnesium calcium ratio for that particular stalagmite, or you have to seal somehow the aragonite with a clay layer, with a very compact, dense lamina, but it has to be impermeable to the water from the top, because in most of the cases the recrystallization is made by the same drip water that is formed in the stalagmite. So during some period of low supersaturation, that can be glacial period or very cold events, the water will shift toward undersaturated, and if the stalagmite is porous, can penetrate, dissolve, and reprecipitate your stalagmite. But if you have this impermeable layer, they will save your stalagmite. So it's really a hydrological and porosity problem, the recrystallization.
Yes, in the back. So
here in Brazil, we're going to be seeing the Diagenesis Diablo Cave. And the Diablo Cave's stalagmite has something really nice about transition from aragonite to calcite. And you can see, I'm not an expert in petrography, but you can see that the calcite layers are primary, not secondary.
Yes.
So you have this interbedding of calcite and aragonite. Do you think that you could be using that as a potential proxy for climate?
Yeah, usually, so aragonite is the dry parent of calcite usually. So in most of the cases, because it requires higher magnesium to calculation, you require a lot of PCP or a very slow dissolution in the host rock. So both the process, as Kathleen explained, require slow percolation in the aquifer, so a dry phase. But it's not straightforward. Still, you have to test it because you can have local hydrological accident. So if you clog a feeding stalactite, you will have calcite precipitation in the aquifer, and you will switch to aragonite without having a dry period at all. So it can be just an aquifer problem for one single stalagmite. But when you have a repetition of calcite and aragonite, this is very likely a climate signal, because it's impossible that you squeeze up and down a fracture for many times. So it is likely to be the case.
Yes. Hello, Andrea. Is it possible for calcite and aragonite grow in the same layer? For example, like one stalagmite add aragonite grow around the edge, and in the center is the calcite.
Yeah,
Is it possible?
Yeah, it is. So
It is.
when we are at the interface between calcite and aragonite, the crystallization of calcite in the center area will increase the magnesium calculation of the water flowing on the flame. And so there you can start having aragonite. The problem is in some cases it's difficult to distinguish a primary calcite and an aragonite interfingering from a secondary one, because what happens is that the next layer of calcite will tend to dissolve and recrystallize the aragonite. So in most cases, when you have a lamina which is made by aragonite on the flank and calcite at the flat part, at the contact you have some recrystallization. So the very flank part is original, but the contact is a diagenetic calcite.
Yes.
And you can still see some aragonite needle relics in it.
Okay, thank you.
Thanks. So, you said like ACC is very unstable.
Yes.
Yes, but I read the people. Some people say their speleothem is formed of ACC. So how it form? I'm very
Yeah.
because it's very
Because they sample the very phase that is growing. So amorphous calcium carbonate is unstable. So you do not have any stalagmite made up of amorphous calcium carbonate. You just have a tiny crystal. In some cases, are still preserved within the speleothem, but are very tiny. So unless you use a very high transmission electrode technique, you are not able to distinguish them. But if you perform the TEM grid experiment in the cave, you can grow them, and you can observe straight away on your grid. And in that case, you know that you had amorphous calcium or battery precursor in your speleothems. Because they have a different also fractionation for the stabilizer. The fact is usually they are a tiny amount in the final calcite product. So are almost irrelevant, I would say, but it has to be tested because there are not many studies about these forms in speleothem so far. So we are still in the very beginning of investigation of these polymorphs in stalagmites.
Thank you so much.
I have a question following the Professor John. So I did some petrography I found like there is a continuous growth of aragonite crystals, but there is some irregular calcite along the flanks of the stalagmite. So how it comes?
It depends how the calcite works. If it's a secondary calcite, in some cases, in some caves, are related to flooding events. So you have flood water passing through and around the stalagmite, and you have recrystallization on the flank. But it depends. The other is a clay coating, can have the same effect. So it recrystallizes towards calcite. So any changes in the environment will tend to shift the aragonite towards calcite equilibrium.
Thank you.
Thank you very much, and thank you for the questions also. Now we will start 2 workshops. So find your respective group, and one is workshop with Andrea, and the other workshop is with Annabelle. So thanks again.